Begin with a word of prayer. Heavenly Father, we thank you for this morning. We thank you for your forgiveness each and every day. We ask that you'd guide our steps today, help the students to understand the material, and I just pray again that they would ask good questions as they think of them, and that you be glorified in what we do, Lord. In your name I pray. Amen. So any questions? No? All right, let's look at some examples today. So we're continuing with graphing with rational functions. Let me do one here that has something kind of interesting. So here we go. It's y equals to f of x equal to, let's say, x plus 3 over, rather x squared plus 3 over, let's see here. I'll make that a 2x. There we go, 2x squared plus 3 divided by x minus, let's say, rather x plus 4. No, not 4. Sorry, I have trouble making decisions in the morning here. 2. We'll make a 2 there. Okay, there we go. So, excuse me. As you look at this rational function, can you tell me, is it factored? Can we factor this more completely? What do you think? That's the first order of business, right? Factoring. See, I would say we can't factor this more. I've got something squared plus a number. That's a prime pattern. So like basically the square is already completed. There's nothing more to do. We're kind of stuck with it. We need complex numbers to factor that. So more to the point, the numerator can never be 0, right? The smallest that expression could be is 3. You put x equal to 0 into it, you get 3. This can never be 0, the top part, right? The bottom part can be 0 when x equal to minus 2, right? What's the domain of this function? What's the domain of any rational function? The answer is negative infinity to infinity, and then take away all of the numbers which make the denominator 0. So in this case, the domain would be minus infinity all the way over to, see, this is problematic when we get to minus 2, right? So this would be the domain. We have to exclude minus 2 because we get division by 0 there. So the answer to the question I just posed is this. The domain of the rational function, whatever one you're talking about, it's going to be all numbers except for those which make the denominator 0. All right? Okay, so there. Anyway, my point to you is that there's only one critical number here, right? The critical number is minus 2. All right? And so you tell me what goes on with the signs here. Excuse me. If I put in like, I don't know, 0, I get 3 halves, right? So I get, oh man, look at that. Look at that. Oh, that's bad. It's bad. Let's see here. So I get plus over here. And then what happens when you cross minus 2? Do we flip signs? I think we do, right? Because there's only one copy of it, so we expect to go plus to minus here. If in doubt, plug in minus 3, see what happens. You get a positive number up top, and you get minus 1 on the bottom if you plug in minus 3.
And you figured that out like by substituting the percent, right?
Mm-hmm. Well, I figured out there's two things you can do. You can plug a number in someplace, and then you can go from that place to another place by looking at the factors. So here there's just the x plus 2 factor. There's just one of them, so we flip signs. So we can both plug numbers in and we can use the sign flip theorem. So anyway, there it is. Now, this one is improper, right? It's not a proper rational function because the numerator has larger degree or equal degree, in this case larger degree, than the denominator, right? So I have to do long division in order to really graph this thing properly. I guess I'm going to do it here for a change. So let's see here. We're dividing x plus 2, into 2x squared plus 3. How does that go? Let's see here. So to get this x from 2x squared, to get 2x squared from the x, I need 2x up here, yeah? Then I multiply this times that. That gives me 2x squared. 2 times 2x is 4x. I subtract. And that gives me minus 4x plus 3, right? And then, in order to get this minus 4x, from that x, I subtract 4. So 2x minus 4. Then minus 4 times x is minus 4x. Minus 4 times 2 is minus 8. I subtract that, right? So the minus 4x is canceled, and you get 8 plus 3, which is 11. That's your remainder, because 11 has smaller degree than the divisor of x plus 2, right? And so this means, what does this mean? This means that f of x is equal to 2x minus 4, all right, plus 11 over x plus 2. So for large x, right, this is essentially f of x as x goes to plus or minus infinity. So like the graph of this function in the big picture of things, the graph is just the line y equals 2x minus 4. Now that's a lie, it's not that, it's something more complicated than that, but the function, it tends to that for large x. So let me sort of hang our hat on the graph with that this time. So what does 2x minus 4 look like? What's the graph of y equals 2x minus 4? I'll do it in dotted line in blue. Y equals to 2x minus 4 is, the asymptote. For y equals f of x. So can you guys tell me what y equals 2x minus 4 is? Is it a parabola? It is not, right? What is it? I'll do the easy part. Its y-intercept is minus 4, right? What's its slope? 2. This is a line, right?
Yeah.
So it's a line with slope 2, and so it's something like all right. Oh man. Poor planning on my part, guys. Well, I'm just going to make do with it, all right? I'll do the best I can with my poor choices here. You'll see why it's a poor choice in a minute. Okay, and then where's the vertical asymptote for this thing? See this? X plus 2 unopposed in the denominator makes x equals minus 2, the vertical asymptote. So right here, so this is your x equals minus 2 vertical asymptote. There's no horizontal asymptote in this thing, all right? And what goes on is the graph looks, see, this is where poor planning on my part, guys. But, so like, it's down here, all right? Okay, down here, and then up here. And what's the if I did this right, where does it cross the y-axis? F of 0 is what? 0 plus 3 over 0 plus 2, right? So the y-intercept is 1.5. So it should be about right here if I'm trying to graph things carefully. So it should do something like So if I can make my graph again, just do it again here without numbers and stuff, just to give you a better sense of the shape. It looks something like this, right? And it probably, that's not to scale, but this is roughly speaking what goes on here, yeah? I'm not sure my second picture was much better than my first, but anyway, I tried. Yeah. So what kind of asymptotes are these? It's not horizontal asymptote, right? What do you say when you have an asymptote for the function that's not a horizontal line, right? But it's this. It's a line, right, with slope 2. This kind of asymptote has a special name, and I don't think it's especially obvious what that name is, but this is called an oblique asymptote. Any of you English majors? So I guess not. There's no one here to explain this to me then. Like, why is it oblique? I don't know. You're like, you could Google it. That's true, I could, I guess. But anyway, any questions? Why did this not happen to us in many of the examples we've looked at so far? Like, let's look at another example here where this will not happen. Example 2. Suppose we have f of x equals to x minus, let's say x squared minus 2x plus 1 divided by x squared minus 7x plus 8. And I need to make this, I messed up the top, guys. I'm sorry. I meant to make that a, no, it's fine, it's fine. And then I'll take all of this and I'll multiply by, let's say, x minus 3 squared. All right, there we go. Let's do this example. Let's graph that. Okay, so here, what are we up against? We need to factor, right? So first order of business is to factor completely, right? But once we do that in example 2, it's going to go better for us. I mean, it's not as nasty an example in the sense that the numerator has degree what? Oh, by the way, guys, I'm going to make a handout on the method that we're using right now to give to you guys. I'm not done with it yet, obviously, but when I do that, I'm going to start using the notation that this is n of x and this is d of x. So I'm going to use n for numerator and d for denominator. I was using, like, I think p and q for you guys, which is, first of all, they look a lot alike, which is not a great choice, right? So I think n of x and d of x is a better choice for this class. So I'm going to start using that as my sort of default. That's my numerator. That's my denominator, okay? So when you look at the handout, you'll see that. But anyway, so n of x, d of x. What do those factor? They factor, right? How do they factor? I think we can do that. X minus 1 squared, yeah. And downstairs we got what? We got a x. Oh. Oof. Who here wants to make that a minus 8 rather than a plus 8? Anybody? If that's okay, I would very much like to change that to a minus 8. Sometimes this happens, you know. That is a freedom that I am allowed, that you are not. Okay, so I think that'll make life go better for us here. Otherwise, I'd have to complete the square. It's an ugly one, okay? And we can come back to one of those today, but not yet, okay? So this is x minus 8, yeah? Times x plus 1, yeah? See, when I multiply those two, that gives me back x squared minus a 7x, and then plus an x, and then minus 8, which is what I have. Okay, so there we go. And then, of course, there's still the x minus 3 squared, right? Okay, let me just tell you what's going to happen here, because this is the easy case. Here, this gives me x-intercepts at 1, 0, right? Because I have a, you know, the numerator is 0 when I plug in 1. And if the numerator is 0 for a fraction, the fraction's 0, okay? So that's the x-intercept. The denominator, on the other hand, vertical asymptotes all around, all right? So we've got x equals to 8, or x equals to minus 1, or x equals to 3, all vertical asymptotes. And I was thinking about it. Maybe this is a better notation for you guys, right? Just to say what you're going to do once you get to this point, so that you can kind of like organize your thinking as you're going to the graph. Now, of course, that alone is not enough information to make a good graph, right? We need to make the sign chart so we can keep track of where is it plus, where is it positive, where is it negative. So let's do that. What comes first? So the critical numbers are what? The places where either the denominator or the numerator are 0 are at what? 1, 8, minus 1, and 3. Yeah? So I've got minus 1, 1, 3, 8. So you guys help me out. What are my pluses and minuses here? Everybody top hat? I've got 18. 1, 2, 3, 4, 5. I think everybody top hatted. Woohoo! I'll put this thing away. And now someone new will enter the room. That's usually what happens. Okay, so you guys help me out. Do we start out plus or minus? What do you think? Like all of my examples so far, right? I have made it so it's essentially the leading coefficient, whatever that means. That's not exactly a thing here. No, no. It's plus. So if think about plugging 9 into it, for example. If you plug 9 into this expression, that's positive. That's positive, that's positive, that's positive, right? Like 9 minus 3 is 6 squared, 9 minus 8 is 1. Everything's positive, so if it's all pluses, it's positive. I will eventually give you guys an example where this case starts out negative, you know? If I remember, maybe next example will work like that. What happens at 8? Do we maintain the sign or do we flip the sign? So the 8 comes from the x minus 8, right? There's just one of them, so we flip the sign. We go plus to minus, all right? And then we get to 3. Where's 3 coming from? 3 is coming from the x minus 3 factor. That's squared. That means that we maintain the sign, don't flip. Even number of minus 3 factors there. X minus 3 factors, rather. We get the 1, right? 1, be careful, corresponds to the factor theorem to what? To x minus 1, right? How many x minus 1 factors do I have in the expression? I have 2, right? So again, keep it negative here, all right?
So why do you keep it negative?
Because we have x minus 1 squared.
Okay.
So it's an even power. So same essential logic as with the polynomials. If we have an even number of the factors, we maintain the sign. If we have an odd number of the factors for the given critical number in discussion, we flip the sign. And and so like the difference is here we could have factors appearing in the denominator and numerator, like in the hole in the graph kind of examples. Yeah, and then you have to count the total number of factors above and below. That's how it works. Okay, so then minus 1 corresponds to x plus 1. There's just one of those. We flip the sign again. All right. Okay, so as a double check on our calculation, let's see what 0 is. What is f of 0? Sometimes it's nice to find a y-intercept, yeah? F of 0, you plug in 0 into the formula, right? What do you get? You get 1 over minus 8 times minus 3 squared. In other words, you get minus 1 over 72. So the y-intercept is pretty close to 0, right? So I'm not going to attempt to. I don't think I'm going to attempt much of a vertical scale here. Here we go. Let's graph it. So what do I want to keep in mind on my graph? Of course, all of these features, right? So 1, 0 is a x-intercept. So you got your x-intercept right here. You've got vertical asymptotes at where? At minus 1, right? And where else? At 3. And at 8. And so now we can make the graph, yeah? Oh, well, one other thing I shouldn't neglect. What's the asymptotic behavior for this function? What happens as we go really far out? What's the asymptote for this one? Notice the asymptote is just y equals 0 here. How do I know that? I know that because we have the degree of n of x, yeah, is what? What's the degree of n of x? What's the degree of the denominator? You guys tell me. 2 for the numerator. Very good. And the denominator?
Would it be squared, or do you have to go by the first expression?
It's the whole thing together that we have to think about. What is the degree of a polynomial? It's the leading, it's the, whatever power has the non-zero leading coefficient that's biggest, right?
So 2 x squared.
So 2, well, think about this. If we took the denominator, right, this here, and we multiplied it out, what will be the largest power that appears? X times x, so you have x times x times x squared stuff. So this is x to the power 4 plus junk. So the degree of the denominator is just 4. Okay, so that makes the denominator wins. Anytime the denominator has a degree which is strictly larger than the numerator, you don't have to do the long division or think that hard about it. The asymptote for the thing is 0. Eventually the denominator wins and it sends the whole thing to 0. All right? There's a theorem maybe I should tell you, because you guys are thinking, you're not thinking fast enough here about degrees. There's a theorem about degrees. What's that theorem? Here's the theorem for you. Theorem. If f of x has degree of f of x equals to m, and g of x has degree of g of x equals to n, then f of x times g of x has degree equal to m plus n. In other words, you can figure out degree of a product of polynomials by simply adding the degree of each polynomial forming the product. So like when I figure out the degree of the denominator here, I go degree 1, degree 1, degree 2, 1 plus 2 is 4. I'm done. All right? Like you don't actually have to think through, if you don't want to, the multiplying out the x's. But that's, I mean, it's about the same trouble really. But anyway, this is something you need to be able to think through without expending a lot of mental energy, because it's important to like the thought process here. You need to be able to recognize when the denominator has the same degree as the numerator or not. All right? It's not a big deal, but it's something we have to be aware of, okay? So then what's my graph look like then? So we've got an asymptote of 0, so we kind of drift into y like this. We blow up at the vertical asymptotes, so this is how my graph starts if I'm going left to right. Like this, all right? And then I'm negative. I go through 1. What happens at 1 though? See that? I stay negative at 1. What's it doing at 1? What's it doing at 1? You guys tell me? That 1 is coming from that, you know, x minus 1 squared up in the numerator rather. It actually bounces again. So it bounces off the x-axis is what's happening there. And my picture's not quite right. Like it's like it's pretty bowed up here. Like this isn't quite doing it justice, because that y-intercept is where? The y-intercept is what? We figured out minus 1 over 72, right? So like to the scale of my graph, this point should be like just hugging the x-axis practically, you know? So it's not quite accurate, but you guys get the point, yeah? So I'm going to sacrifice scale for visibility. So that y-intercept is minus 1 over 72 though, technically. And then what happens at 3? What are we on the other side of 3? We're still negative, aren't we? It's like a volcano that opens down, or an infinite pit, if you like. And then what happens at 8? We never get back through the x-axis, right? Remember, one of the guiding rules here is we can only cross the x-axis where? We can only cross the x-axis in the graph either at where there's a vertical asymptote, right? Or where there's a hole in the graph at the x-axis, or where more often there's a x-intercept. The larger point, to summarize, you can only cross the x-axis at critical numbers. So that's very you know, restricting on how you make the picture essentially. And then you also have to blow up or blow down at the vertical asymptotes. That pretty much guides the picture you can draw. So that's why I can't cross the x-axis between 3 and 8, right? Because why? There's no critical number there, right? There's no opportunity for the function to be 0 or undefined between 3 and 8. It's just negative. So it's got to stay negative, but it's got to blow up down here and it's got to blow down there. So it's got to bend like that. That's the only thing I can do logically. Then over here, we're positive again, but we're drifting to 0 eventually. So it's got to look something like this. Okay? I personally think this example is much easier than my example 1, because example 1, you know, the oblique asymptote thing, to actually make a good picture with that, you have to do a lot of planning in terms of like choosing a scale which allows you to, you know, see what you're doing well. As you can see, I didn't fare very well here, did I? So, any questions? We do have time for questions. I mean, so at this point, guys, I should kind of keep score in here. We have pretty much covered, as far as I can think of. I mean, I'm going to sort through the homework here when I get a spare moment to think. But I think we've pretty well covered the material that's on quiz 2. Yeah? So what's, you know, basically we need to know how to do what? Graph polynomials, graph rational functions like we're doing right now. Yeah? We need to know how to graph every quirk and feature about the parabola, right? We learned all kinds of stuff about parabolas that we can kind of expect to see on quiz 2. And hence, and what is quiz 2? Quiz 2 is a warm-up for test 2, isn't it, right? So if you get something wrong on quiz 2, you need to stop what you're doing, figure out what went wrong, and fix it before test 2 so that you don't, things that don't go badly for you. Of course, I want you guys to just get everything right on quiz 2 so you can, kind of relax and go, okay, well, I'm ready for test 2 then. That would be wonderful if that happened. But if it doesn't, it's not the end of the world. This is why I make quizzes worth relatively little of your grade compared to the test, right? Okay, so example 3. Here's another one. Suppose we had f of x, we're going to graph f of x equals to x squared plus 4x plus 5, all right, times x minus 1 over, let's see here, x squared plus 4x minus 5, all right, times x plus, let's say 2. So here, there's something I've shared with the other sections, I haven't shared with you guys yet. But this is kind of a special, what's the degree of the numerator, what's the degree of the denominator? In this one. We've got what? A quadratic times a linear, and this is also a quadratic times a linear. So you have 2 plus 1 is 3, 2 plus 1 is 3, degree 3, right? So we're in the case that, if you just go by my algorithm I wrote for you guys last time, we'd be looking at long division, right? But the thing is, when they actually have equal degree, there's a way around long. You don't actually need to do the long division. In this case, there's a simpler thing to do. And so here's the theorem that we can look at, and I'll share it with you. If we're looking at y equals to, like, say, a sub n x to the n plus, plus a1x plus a0, and we're dividing by b sub n x to the n plus plus b1x plus b0. So what I'm saying is we're looking at the graph of a rational function where both the numerator and the denominator have degree n. So they're matching, right? Then what you can do is you can divide the top and the bottom by x to the n. So if you look at that, that's an plus plus a1 over x to the n minus 1 plus a sub 0 over x to the n, and I'm dividing the top and the bottom of the expression both by x to the n. So like the next term that I haven't written would be bn minus 1 over x, and then finally ending with like b sub 0 over x to the n. So if you think about that expression, what happens is x goes to plus or minus infinity with all that. So as x goes to plus or minus infinity, all of this stuff, right? And all of this stuff, what happens to it? You're looking at numbers over a really, really big positive or negative number. So that is really, really small compared to the leading coefficients, right? Everything I've circled in red is minuscule in comparison to these two. So this just goes to a sub n over b sub n. All right, in other words, in short, the theorem simply says this, then y equals an over bn is the asymptote of y equals f of x. Well, y. Let's just say it's the asymptote of this expression. Okay, I didn't give it a name, so my bad. Anyway, so here's the theorem. Like, the thing under it is just the proof of the theorem, so you guys can ignore that if you don't If you don't care about why it's true, this is just why it's true. All right? If you don't care so much about the why and you're just interested in the how, this is how to find the asymptote. For equal degree, you just look at the leading coefficients, take their ratio. All right? So for the problem we're looking at, what is the leading coefficient of the numerator and the denominator here? If you look at it, we've got like x to the power 3 plus stuff, right? And then x to the power 3 downstairs plus stuff, right? So what's the asymptote? It's just the ratio of 1 and 1, right? Do you want me to make it more interesting? I could add a number. You guys are... Let's see here. So if I stick a 3 right here, yeah? If I stick a 3 right there, what's it do? It puts a 3 in front of the leading coefficient at the top, yeah? And so with that, this gives me, by the theorem, y equals 3 is the horizontal asymptote for the graph that we're looking for. All right? That's all I'm saying. So you don't need to actually, so this is welcome news, right? Because if you think about the process of doing long division on this kind of problem, it could get kind of troublesome, you know? The reason for that is, in principle, to do the long division, you might need to at least think about multiplying these things out. And you don't really want to do that if you don't have to, right? I don't want to multiply these things out if I don't have to. So having this theorem is a nice workaround for this kind of example. And this is a kind of example I might put on the test, because this is not too bad graphically speaking. You just have to look at the ratio of the leading coefficients, all right? So, okay. Let's forge ahead. So what's the next thing? We're supposed to factor completely. How does the numerator factor? I promised you we'd get back to completing the square. That's happening now. This is x plus 2 quantity squared plus 1. So when you complete the square on x squared plus 4x plus 5, you get x plus 2 quantity squared plus 1, right? Because if you think about it, you're going to subtract the 4, but when you add the 5, you get back to 1. If you don't believe me, multiply this out right here, right? Think about multiplying this out, FOIL it out, you'll get back x squared plus 4x plus 4 plus 1, which is exactly x squared plus 4x plus 5, right? So does this have any critical numbers? The answer is no, right? This is a prime polynomial. It doesn't cross this quadratic, doesn't cross the x-intercept. There are no critical numbers coming from this first factor. It's just sitting there being annoying, yeah? Okay, so, and the quadratic and the denominator, man, it looks so much like it, doesn't it? I mean, what's the difference? What'd I do? Changed a 5 to a minus 5. What's the difference? What difference does it make? Someone said that once. Let's see here. X plus 2. Makes a big difference. So here, I'll put an x. You guys factor for me, x. This right here, how do I factor? X plus 5. Very good. X minus 1. Yeah. So there we have it, okay? Okay, so now let's take stock of things. What are we looking at here? Let's say what's going on. So we've got critical numbers. The critical numbers are what? 1, right? Minus 5 and minus 2. And you know, what's the situation here? 1 is a hole in the graph. Right? Why is that? Why is 1 going to be a hole in the graph? Because you have x minus 1 in the numerator and you have x minus 1 in the denominator. Right? What's the reduced function here? The reduced function of x is everything except for the x minus 1s. So it's like 3. I'm going to uncomplete the square if you don't mind. Well, fine, I won't. X plus 2 squared plus 1 divided by x plus 5 times x plus 2. So what I'm doing here This is everything except for the hole in the graph factors, which we're canceling. So like the reduced function is what you get from simplifying the formula by canceling out the things causing the hole, all right? And so where is the hole? The hole is at where the reduced function would be at the hole value. So f reduced of 1 is what? 3 times, well, that works out to 4. Wait a minute, that works out to what? My bad. Plug in 1 in that expression, what do you get? We get 3 squared plus 1, right? Divided by 6 times 3. What is that? The 3's cancel, yeah? And it looks like I got a 10 over 6, also known as 5/3. So the hole in the graph is actually going to be at 1, 5/3 is hole in the graph. So to find the hole in the graph, you have to look at the reduced function, plug the number in, that tells you where it is. All right? And then how about -5? What's the situation with that? -5 and -2, they're actually both the same, right? Both of these guys giving us what? X equals -5, x equals -2. These are vertical asymptotes, right? How do I know that? Because the x plus 5 and the x plus 2 factors only appear in the denominator. So those give you division by 0 in the formula. Therefore, those are vertical asymptotes, yeah? Now what? Now we can, well, I'm almost to the point of graphing. I guess I still owe you guys a number line, right? So what is my number line? What do I have to put on there? -5, right? Let's see here. -2. And let's see here. If that's 3, so it should be by here. 1. That's it, right? I will eventually remember to make an example where we start with something other. I think, again, we have pluses on the far right, right? What happens if you plug in 2 to the expression? If you plug 2 into this, right? Positive, 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 and well, it's easiest to look at this one here, right? If you plug 2 into this, it's all pluses. So we start out plus. Now, do we maintain or flip the sign at 1? What do you guys think? At 1, do we stay plus as we go to the next region, or do we flip to minus? Where's the 1 coming from? The 1 is coming from this x minus 1 factor, and also what? That x minus 1 factor, right? There's 2 of them. That means we don't flip signs, we stay on plus. Right? And that is consistent. That's consistent with the fact that we found that the hole in the graph was at 1, 5/3, right? The hole in the graph is where it's positive, so we should be positive here. That makes sense. How about at -2? Do we flip? Do we stay? What goes on at -2? -2 is coming from what? From the x plus 2 factor. Is there any other one? You're like, oh, well, there is. There's another x plus 2 factor here. This does not count, though, okay? This is the appearance of x plus 2 and like a completing the square additively. This does not count in this logic. What we need is an x plus 2 multiplied, like an actual factor to either the numerator or the denominator. X plus 2 is not a factor up here. It's a summand in completing the square. It's something else. It's not technically a factor here in the numerator. So only one x plus 2 factor, because it's multiplying the whole thing. Right? If the thing is not multiplying everything in its either respective numerator or denominator, it does not count as a factor. X plus 2 is a factor here. There's only one of them. We flip signs. And then x plus 5, that's less to think about. There's just one of them here. We flip signs again. So we go from minus to plus. Right? Let's see here. And that's, I think, all I need to graph it. All right, so here we go. Y-axis is somewhere up in here. Here's my x-axis. Let me put in my vertical asymptotes. Where are they at? Well, I just get done saying -2. And where else? -5. Vertical asymptotes up in there. And what's my asymptote here? Asymptotically, remember y = 3 is the horizontal asymptote, so I'm drifting eventually to like here. So this, I want to eventually drift into this y = 3. That's my horizontal asymptote for the graph. Anything else? Well, we know where the hole in the graph is, right? Where is it? I guess I could add that. It's at 1, right? It's at 1, 5/3. 5/3 is what? That's like 1.7-ish. So it's kind of just a little bit above the halfway mark here if I'm careful. So it's somewhere like here, right? It's not a lot to go on, but there it is. Okay, so let's get started. So we start with over here like this, right? And then what? I'm negative. I've got vertical asymptotes. Where? So let me draw something. You tell me whether I'm right or wrong. Right or wrong? If I put this on the test, should I take off a point? Why or why not? I mean, I think maybe I deserve some partial credit. I've got kind of the idea, right? I mean, I know that it's a vertical asymptote, so I got to be like getting close to the vertical asymptote and blowing up, either blowing up or down. So that part of it's right. But what's wrong? Crosses the x-axis, right? If it does this, that means I've got x-intercepts here and here, and they can't appear on the graph without also appearing on my list of critical numbers, and hence the number line, right? But I don't have x-intercepts there, so it can't look like this. It has to look more like this. Now, you might ask, where does it turn around? Like, how do you figure out what's the top of the heap there? You know, like, how do you figure out the sort of the vertex of that thing? If that terminology makes sense. Do you guys know? How do you find the top of that? So what you're looking for is you're looking for a point on the graph where if you put a horizontal line over it like this, it just touches the graph one place, kind of like that, you know? You're kind of looking for that. So you're looking for what's called a horizontal tangent line. To find that point, you'd have to do this. You'd have to take df, dx, and set it equal to 0. Where the places where df dx is equal to 0 will tell you where the graph turns around. What is df dx? Some of you guys saw this in high school, I think. That is the derivative, right? So we set the derivative equal to 0 to find places where it turns around. But we don't do that because this is not calculus, right? So my point to you is to figure out like where that happens is above your pay grade, right? It's above my pay grade in here. Like we can't do that. We don't have the technology we need to find those things, which is this. Now some of you will take Math 126 after this, right? Maybe. There exist students who take this course and then 126. Such students will get the joy of actually looking at the derivative and maybe solving some. This problem might be too hard. I don't know if this problem is too hard for 126 or not. It might be in terms of the calculus, but all right, enough. So it's got to look more like this. Again, I don't really know where it turns around. I'd have to do some like searching and plugging in points to figure that out. What happens as we cross the -2 vertical asymptote? We're over here. We're positive again, right? And what happens is you kind of have to connect. I'd say connect the dot, but it's kind of like that. You don't really connect it. You just get to it, and then what happens is we have to kind of turn around and then asymptotically go like that, most likely. Right. It is possible that the graph crosses the y equals 3 and then comes back down after it. I really don't know without further investigation, but it looks something like this. So all we can be certain of with this method is like where the vertical asymptotes are, where the x-intercepts are, and the graph being on one side or the other of the x-axis. Those things we can be sure of with the data that we have. Places where it like maximizes or minimizes, like where is this turning point here? I know it's got to be somewhere because it doesn't cross the x-axis again, right? If it doesn't cross the x-axis again and it drifts up to 3, it has to kind of bend back like that. Where exactly does that happen? That we can't figure out without plugging in numbers and stuff. Okay, anyway, I hope I'm explaining to you not just what we can do, but a little bit about what we can't. So, yeah.
So on the quiz, the test, you won't take points off if we don't do like the points shown where.
I do want some things labeled, so like I might say something like graph the rational function. Be sure to explicitly label any vertical asymptotes, hole in the graph, and x-intercepts. And I might, if I'm not being stupid, I will force you to use a certain scale and give you some like graph paper on the actual test that you can kind of work on, so that I know what the right answer looks like, independent of how you chose the scale. With 100+ college algebra students, I want to set the scale the same for everyone. Otherwise, I have 100 different scales to sort through. And if I assign 3 graphing problems, then it's 300 scales to sort through. And if there are 5 graphing problems on the quiz, then there are 500. Anyway, you get the idea. Of course, my ultimate goal always with a quiz or test is to see if you've understood what we have said in class and tried to work out together. And I hope the homework is also, pushing you towards that goal. I don't make those problems, right? I'm stuck with what the textbook gives me. Some of those are like really interesting. Some of them like a little bit less so. Some of them are very rudimentary. I hope you enjoy those ones, right? Like you've got 8x to the 5th. What's the degree? That's like a problem in your homework, right? It gives you 8x to the 5th, and then it's like, here's a box. Put the degree, That's one of your homework problems, right? How do you do that problem? You look at it, you go, 5, right? Done. Which is kind of like a really, really stark contrast to like what we just sorted through in any of the examples today, right? Like the level of thinking that's required to do these examples is on a much higher, I think that the logic involved for graphing rational functions in this course is about as hard as this course gets, by the way. Like there's a lot going on here, right? I had to write about a page of notes to explain to you all the quirks and features of our method, right? Especially because these holes in the graph, they require this kind of, fussy thinking. Let's do another one. Anyway, I am hoping to give you, like I said, a handout that hopefully clarifies and expands my... I'm hoping to summarize all of the different things I've picked up on teaching this material this semester, talking to different students, different classes, I've learned things from students as they ask questions, and so I'm going to try to put all those things on the handout so you have it all in kind of one place, a summary of how to graph these things. All right, so here we go. Let's try to graph y equals f of x equal to, I don't know, how about 9 minus x squared over x squared plus 4x plus 1. This one is annoying in ways that we haven't really faced yet, okay? And a couple different things. So we factor, right? So factoring this gives me what? 3 plus x, 3 minus x, yeah? So first of all, the factoring is kind of funky, right? Because we get a minus x squared for the first time in the factoring for a while. So that's how that factors. And but the denominator, how's that factor? Let's complete the square down here, right? So we have x plus 2 squared minus 4 plus 1. So I completed the square there. All right? So that's what? So it might be smart to go off to the side and just factor the denominator separately, but I'm just going to keep going here because I've got a little bit more board space to work with. So I've got x plus 2 squared minus 3, right? Is that prime? Unlike my previous example, which had a prime numerator, right? This one is not prime, right? That factors. How does it factor? Can you guys factor this? Remember what we do? Think of the 3 as the square root of 3 squared, right? And so the way what we got here is 3 plus x times 3 minus x, all divided by x plus 2 plus the square root of 3, x plus 2 minus the square root of 3. All right. How about the horizontal asymptotes? Are there any horizontal asymptotes going on for this problem? But first, are there any questions about the factoring I just did? I mean, this is the harder part of the factoring idea, right? But what kind of situation are we looking at here in terms of horizontal asymptotes or oblique asymptotes or whatever? What kind of asymptotes are we up against here? What's the degree of the numerator? It's what? 2. The degree of the denominator? 2. Oh, hey, this means we could use the theorem, right? So our handy-dandy take the ratio of the leading coefficients theorem. So by easy way out theorem, there, I'll call it that. I gave it a name. Y equals to, what are the leading coefficients here? The leading coefficient of x squared is minus 1, and downstairs we have 1, right? So we have a horizontal asymptote of minus 1 for this graph, all right? What are my critical numbers? Critical numbers are minus 3, 3, and then minus 2, plus or minus the square root of 3. Right? Which one of those gives me vertical asymptotes? Which one of those gives me x-intercepts? That's just asking the question, which one came from the numerator? Which one came from the denominator? Okay, so like these two give me x-intercepts. These two give me vertical asymptotes because they're from the denominator. The other ones are from the numerator. We can make our sign chart, although I think it's in your best interest, in my best interest as well, for us to get a calculator out and just make sure we've got a good sense of where those numbers are, right? Because what is the square root of 3? How does it relate to 2? Is it smaller? Is it bigger? And what's the situation there? Yeah, it's square root of 3 is, I think, 1.7 something. 1.7